Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Bridging Between Algebra and Calculus series and concerns exponential functions. This guide explores the basic properties of exponential functions and how to use them in calculations using examples from biology and economics. It also explains the connection between exponential functions and logarithmic functions. Introduction. Exponential functions are an extremely important family of functions in both pure mathematics and where mathematics is applied. They are similar to the power function, y equals ax to the power n. However, in an exponential function, the unknown variable x is part of the index of the function, not the base. You can write a general exponential function as y equals a multiplied by b to the power kx, where b is a number called the base and the variable x forms part of the index or exponent of the function. This formula also contains two constants, and it is important that you understand their meaning properly. The first constant, a, is the value of the exponential function when x equals 0, and is where the function crosses the y-axis. The other constant is k, and this controls aspects of the shape of the function, such as its steepness, and importantly whether the exponential function describes exponential growth or exponential decay. For exponential growth, the value of k is positive. K is greater than 0. For exponential decay, the value of k is negative. K is less than 0. Exponential behaviour is common in applied mathematics. For example, it is seen in compound interest in economics, reaction kinetics in chemistry, population dynamics or spread of infection in biology, nuclear chain reactions and radioactive decays in physics. The simplest example of exponential growth can be seen in the graph of y equals a multiplied by b to the power x, shown below, which is obtained by setting k equals 1 in the general exponential function. As x increases, the value of the exponential function increases rapidly. The x-axis is an asymptote. See study guide, sketching a graph. This is because, as x gets more negative, the value of y gets closer to 0. However, there is no value of x which gives the function a value of 0. So the graph never crosses the x-axis. There is no asymptote as x approaches infinity. The graph also crosses the y-axis at a, because when x is equal to 0, y equals a multiplied by b to the power 0, which equals a. A is indicated on the graph by the arrow. The simplest example of exponential decay can be seen in the graph of y equals a multiplied by b to the power minus x, shown below, which is obtained by setting k equals to minus 1 in the general exponential function. As x increases, the value of the exponential function rapidly approaches 0. Again, the x-axis is an asymptote. This is because as the value of x increases, the value of y gets closer to 0. However, there is no value of x which gives the function a value of 0. This graph is the graph of the function y equals a multiplied by b to the power x reflected in the y-axis. There is no asymptote as x approaches negative infinity. The graph crosses the y-axis at a because when x is equal to 0, f of 0 equals a multiplied by b to the power 0, which equals a, as indicated by the arrow. Exponential functions and the number e. An important example of a family of exponential functions is when the base is equal to the special number e. This general function, sometimes called the natural exponential function, is very common in mathematics, economics and science, and is written as y equals a multiplied by e to the power kx, where a and k are constants, as explained above. The number e, always lowercase, is the symbol for Euler's number, named after the famous mathematician Leonhard Euler, and has the value of e equals 2.71828182885, and so on. It is a common misconception that the e stands for exponential, but in fact it stands for Euler. Euler was the first person to use this notation in the 18th century, and he was able to approximate the value of e to 18 decimal places. The number e has a crucial role in mathematics, especially calculus, in a similar way that pi is central to geometry, and is both an irrational and transcendental number. See study guide, different kinds of numbers. Examples of exponential behaviour. Values or measurements that grow exponentially exhibit behaviour which increases proportionally over a constant amount of time, for example. As a direct effect of this, the observation you are measuring grows rapidly. You can see this by thinking about this simple system. Start with the number 5 and double it every 1 minute. The sequence below shows the numbers that you have as the minutes tick by. 5, 10, 20, 40, 80, 160, 320, 640, and so on. The numbers are said to be growing exponentially, and you can probably see that they will get extremely big extremely quickly. The exponential function which describes this system is y equals 5 multiplied by 2 to the power t, where the variable time is represented by t. The number you get after a certain time is y, and depends on raising the base 2 to the power of t. The 2 comes from the fact that you are doubling, and the value of a is 5 because you started with the number 5. Values or measurements that decay exponentially lose a constant proportion of their value in a given time, for example. Think about the number 4000. If you half it every minute, then you get the following sequence of numbers as time goes by: 4000, 2000, 1000, 500, 250, 125, and so on. The numbers are said to be decaying exponentially. You can see that the numbers are getting smaller, but the rate at which this is happening is getting slower, as the number you are halving is getting smaller each time. More subtly, the numbers in the sequence will never reach 0, as you will always have something left over after you half the previous number. The exponential function which describes this system is y equals 4000 multiplied by 2 to the power t, where again the variable time is represented by t. The number you get after a certain time is y, and depends on raising the base 2 to the power of minus t. The 2 comes from the fact that you are halving, and the value of a is 4000 because you started with the number 4000. Exponential functions and logarithms. If you divide both sides of the exponential function by a, you get y divided by a equals b to the power kx. This is useful because in mathematics there is an equivalent way of writing an equation of this kind in terms of a single logarithm. This is kx equals log to the base b of y divided by a. This piece of mathematics is discussed further in the study guide, Basics of Logarithms. You can move freely between the two types of equations using the logarithmic transformation. Y divided by a equals b to the power kx converts to log to the base b of y over a equals kx, or vice versa. Importantly, exponential functions and logarithms are mathematical inverses of each other. See study guide, Inverse Functions and Graphs. In other words, they undo each other in the same way that addition undoes subtraction. This is extremely useful when you are rearranging or solving exponential equations. Example. In the exponential growth example in the previous section, how many minutes does it take for the numbers to exceed 5,000? The growth of the numbers is given by y equals 5 multiplied by 2 to the power t. So, with y equals 5,000 and a equals 5, you can write, after dividing both sides by 5, 1,000 equals 2 to the power t, which converts to log to the base 2 of 1,000 equals t. Inputting log to the base 2 of 1,000 into a calculator gives t equals 9.97 to 2 decimal places. So, it takes 9.97 minutes for the numbers to exceed 5,000. Like all other exponential functions, the natural exponential function is linked to a logarithm via the logarithmic transformation. In mathematics, this logarithm is called the natural logarithm. The natural logarithm has a base e and is written using the symbol ln rather than log to the base e. So, using the logarithmic transformation, y equals e to the power x converts to natural logarithm of y equals x. Exponentials in action. Populations. It is very common for exponential equations to describe how population size changes over time. Often, t, for time, replaces x as one variable, and the population, p of t, with the subscript indicating the population at time t, replaces the other variable y. In this case, you will often see the exponential function written as p of t equals p of 0 multiplied by b to the power kt. Here, p of 0 represents the initial population, i.e. the population at time t equals 0. Note that p of 0 is the equivalent to the constant a introduced in the general exponential function. Example. The population of bacteria in a sample increases by 10 times every hour. How many bacteria are present after 20 hours if you begin with a culture of 2 bacteria? In this example, you know that you have 2 bacteria to begin with when t equals 0, and so p of 0 equals 2. Your population at time 0 is 2. You also know that the population increases by a factor of 10 every hour, which tells you that 10 is the base. So, the exponential equation for this system is p of t equals 2, the initial population, multiplied by 10 to the power kt. You need to find the population when t equals 20, which is p20. The problem here is that you do not know the value of k. However, you do know that after 1 hour, t equals 1, there are 20 bacteria. In other words, p1 equals 20. You can use this to find k. So, when t equals 1, p1 equals 20, which equals 2 multiplied by 10 to the power k. Which means that, after dividing by 2, 10 equals 10 to the power k, implying that k equals 1. So, using this and t equals 20, you can calculate the number of bacteria after 20 hours. P20 equals 2 multiplied by 10 to the power 1 multiplied by 20, which equals 2 multiplied by 10 to the power 20, which equals 2 followed by 20 zeros. A lot of bacteria. Exponentials in action. The compound interest formula. Exponential growth is an important concept in economics where it is applied to continuously compounded interest and to inflation. When banks advertise interest rates, it is often expressed as R% per annum. So that if, for example, £100 was invested for a year, at the end of the year it would be worth £105. if you got 5% interest paid once only. If the interest is paid continuously, then the money grows exponentially according to the formula P equals P0 multiplied by e to the power RT, where P is the amount of money the investment is worth at the time T, measured in years, for an interest rate R, written as a decimal, and for an initial investment P0. Example: you take out a £100 loan from the bank, compounded continuously with interest at 5%. How much will you have to pay back after 6 months? In this example, interest is compounded continuously for 6 months, and so T equals 0.5 years, at an interest rate of R equals 5%, which equals 0.05 as a decimal, and you borrow P0 equals £100. So, using the formula above, P equals £100 multiplied by e to the power 0.05 multiplied by 0.5, which equals £102.53, which means that you pay back £102.53 after 6 months. Further guidance and information. If you have any further questions about mathematical skills or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor, or make an appointment to see a learning enhancement tutor in the Dean of Students office. You can telephone 01603 592761, email dos.help@uea.ac.uk, or visit our website at www.uea.ac.uk/dos/let. There are further resources on many other aspects of numeracy, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills. This guidance is one of a series on mathematics produced by the Dean of Students office at the University of East Anglia.